हाँ लेकिन सर
Mr. Twarit Patel.
Right, sir. Okay.
Mr. Kumar, please mute yourself. It is requested
Good morning to all of you. Good morning, Dr. Muriel. We're in the fifth and final day of our workshop, the online one-week workshop cum faculty development program on quality engineering and technological advances in materials and devices. We have 4 speakers today. First, we'll start with Dr. Alexis Muriel. Welcome you, sir. And before you start, let me introduce Dr. Muriel. He's originally from Toulouse, France. Dr. Muriel obtained the title of doctor. Interaction. Sorry. He obtained his PhD. He obtained his PhD in material chemistry and electrochemistry of solids after defending his thesis on lithium-ion battery 3D printing via thermoplastic material extrusion at the University of Picardy Jules Verne, Amiens, France in 2020. After working as a postdoc in France for a few months on the same topic, Dr. Alexis now become a visiting he's visiting the University of Texas at El Paso as a postdoctoral research. He's working on a topic related to additive manufacturing of energy storage device. He is a laureate of the prestigious 2021 Fulbright French Research Prize awarded by the French government, US Department of the States. So over to you, Dr. Muriel. You can start your topic.
Thank you very much, sir, for this kind introduction, and thank you for the invitation. It's a huge honor for me to be here. I would like to particularly acknowledge as well Professor Minal Gupta for her kind invitation. Just want to make sure that everything is all right from the technical side. Can you see my screen?
Yes, your screen is visible.
Perfect. Thank you very much. So I'm Dr. Alexis Morel, and today I will talk, as it was said, I will talk about lithium-ion battery 3D printing. That was my PhD thesis topic when I was still working in France in the University of Picardy-Jules Verne in Amiens. And as it was said, I mean, I just moved to recently, 1 month ago, to the University of Texas at El Paso through a US Department of State and French government fellowship called Fulbright. And so here at the University of Texas at El Paso, I will just continue my research on that particular same topic. So I think there are some students actually on the audience today. And so, I mean, I think it was a bit interesting for them as well to understand about the opportunities that are I mean, abroad as well. And so this is, first of all, why I wanted to share my personal background. So I'm from Toulouse, France, as you just mentioned previously. And I started my studies there, you know, bachelor degree, and I was studying chemical engineering, materials chemistry there. And then directly, I mean, during my bachelor, I had the opportunity to go to Mexico once during like 6 months, 1 semester to work there. So that was still studying, you know, on chemical engineering side. And after that travel there and studying there, I mean, I just came back to France and, you know, I was like, oh, you know, studying abroad is something amazing because you learn a lot, of course, language, but also culture and from other people, from other religions, etc., etc. And so this is really, really a huge opportunity. And so if there are some students that are listening on that talk, I mean, go for it. If you have opportunity to go abroad, to, you know, to make part of your studies, even if your plan is to come back to your origin country after, I mean, go for it because you will learn quite a lot. At least I did, and so after coming back to Toulouse, France, I just finished my bachelor degree there, and then I applied to a master, and so that was a master. Maybe you heard about that. This is what we call a master Erasmus Plus. And so typically, this is why I'm sharing the link right now with you, because you have many opportunities from bachelor, master, but also PhD scholarships. And so typically, you will go make your study abroad in some various countries in Europe, and you will get paid for that. So it's like a huge scholarship, and it's quite helpful actually. And so I mean, after finishing my bachelor degree, I had the opportunity to apply for such a master program. So it was a 2-year master program, specialized in energy storage and conversion and materials chemistry. And so luckily enough, I mean, I got into that 2-year master program. And particularity of this kind of program is that every semester you need to spend, like 6 months in one different country studying. In my case, that was materials chemistry for energy storage and conversion. And so, of course, I mean, I studied that particular topic, but I want you to be aware that there are topics in many topics, different topics. So from chemistry to mechanical engineering, with arts as well. So go on this link if you're interested in that, and you will see the list of all of the programs if you're interested in. So in my case, I spent my first semester of master studies in Toulouse, France. And then with all of my class, so we were like 20 students from all over the world, like 20 different nationalities. That was really great for, to understand also the culture from the others. And so, I mean, the whole class, we moved from France after the first semester to Poland. So we studied for 6 months in the city of Warsaw. And then again, I mean, the next semester, the whole class, the same group, we moved to study in Cordoba, in south of Spain, on the same topic, okay, energy storage. And then last semester, that was kind of internship in some laboratories. So right now I know that in the master I've done, I mean, we had opportunities to go to many countries, and also abroad, I mean, also far from Europe, because I know that in the past there was China included as well. And right now there is still USA and Australia. So many opportunities to go there. And so my master thesis particularly, this is when I started working on 3D printing of lithium-ion battery. And I've done that in Amiens, France. So just to enter into more details, because this talk is related, I think this week regarding, new materials like for energy storage, conversion, etc. And so here is a particular link of the master that I did if you guys are interested in that. So this is called MESC, Material for Energy Storage and Conversions. And so this is just what I said. I mean, go for it if you're interested. It's so in my case, that was a 2 years master program. Classes were taught in English with students from all over the world, as I just said. Each semester was spent in different countries. And as I said, I mean, you get paid for it. So it's like, just to give you an idea, it's like 20 kilo euros scholarship per year. So in US dollar, maybe if you're not familiarized with euro, it's kind of $25,000 a year. So you will get this kind of scholarship to go there. So apply if you're interested in that. It's highly competitive, of course, because many students want to go in that sort of program, but it's really worth it. It's really worth it. And finally, last point is that, as you can see, I put joint diplomas. What does that mean? It means that for each university that you will go through during these 2 years, you will get a diploma. So meaning, in my case, I went to France, Poland, Spain. I got a diploma from, I mean, the same diploma, okay, the same master, but it's valid in all of these countries. So it's quite interesting, depending on what you want to do after that. So this was for students, but of course, professors on this particular field, on material for energy storage and conversion, please share this link with your students. Maybe some of them will be very interesting to go for such opportunities. So I mean, I spent after that, I did my PhD thesis in Amiens, France. So in Amiens, France, we have two things. We have a very beautiful cathedral, which is like 800 years, old. And just in front of that cathedral, almost, we have the laboratory in which I was working. So it's called the Hub de l'Énergie, and it's really specialized on energy storage and conversion. There many people, like 100, a little bit more than 100, are working specifically on batteries, on lithium-ion batteries, on magnesium-ion batteries, on sodium-ion batteries. I mean, many different kind of technologies. Also, we have a team working on modeling, you know, the modeling and simulation aspect about that. We have also a team working on photovoltaic, another one in hydrogen storage. And finally, something important is that we have also in this laboratory like a pre-industrial upscale. So we are, you know, I mean, there are some startups, for example, that were kind of initiated within this laboratory and that are still, you know, in phase of development before industrialization, that are still working there. So there, of course, I mean, as you can see, we have plenty of good machines and, you know, characterization technique to work on that. And so that was a very interesting place to work on my topic, which was lithium-ion battery 3D printing. And so after my PhD thesis, finally, and that was 1 month ago, I just arrived to El Paso in Texas to work on that same particular topic on energy storage, materials chemistry, and 3D printing of lithium-ion battery. So then I will enter into the second part of that talk. So why battery 3D printing, right? This is the big question. So all of you are aware about the issues that we have right now. And so we move towards greener, but unfortunately intermittent energy sources, such as wind turbine or photovoltaic. Of course, I mean, these energy sources, you know, for example, if you take into account the photovoltaic panel, during the night, you don't have sun. And so, of course, in parallel with such energy sources, energy storage devices are mandatorily needed. And among them, lithium-ion batteries appeared lately as the technology of choice right now. So, you know, it's kind of funny because right now I'm giving my talk to you, okay, to all of you. And I'm quite sure that less than 1 meter far from you, you have a lithium-ion battery. In your phone, in your laptop, in your watch, okay? And if you are lucky enough, I'm not, you may have an electric car event, you know? So anyway, I mean, these tiny devices have become so popular and so important in our today's life that, I mean, in 2019, even the Nobel Prize in chemistry was given to the pioneers in our field. Those 3 scientists here. So, I mean, why 3D printing? I continue, and so of course I need to illustrate a little bit how lithium-ion battery is working. Okay, so you have different components in it. You have a positive electrode, a negative electrode. Okay, and it's separated by a separator, which is electronically insulator but ionically conductive. And so here, as you can see during this small animation, you can see that the lithium-ion will just make the shuttle between both electrodes, you know, doing charge and discharge of the battery. So commercial lithium-ion battery, here this is the scheme of a commercial lithium-ion battery. As you can see, they are based with what we call a liquid electrolyte. Okay. If you take into account, if you take a look at what you have as battery within your phone, and all of the commercial lithium-ion battery, generally speaking, like 99% of the battery nowadays, they are following a 2-dimensional architectures. So typically, what does that mean? It means that it's kind of, you know, foils that are stacked or rolled together to form the complete lithium-ion battery. And so what was demonstrated in literature is that by moving you know, from a 2-dimensional architectures of the battery toward the 3-dimensional architectures of the battery. Here, for example, you can imagine, you know, in blue, the positive electrode, here in red, for example, the negative electrode, and in the middle, we could imagine to have an electrolyte. Just by moving from 2D architectures toward the 3-dimensional architectures of the battery, it was demonstrated in literature that you can enhance the electrochemically active surface area. And this also will allow this kind of structures will allow to have a lithium-ion diffusion within the three-dimensional space into the wall environment. Instead of just doing the shuttle, like I just showed previously. And so it was proven via some modeling studies that it could enhance greatly the power performances of your lithium-ion battery. So what does it mean? It means that when you want to charge your battery, we could do it faster. Okay, this is what that means, power. So then there is a second goal. So of course, sorry, I didn't say, but this kind of 3D architectures, we cannot obtain it via traditional manufacturing ways. And so of course, there were some attempts done in the past with electrode deposition, etc. But unfortunately, there were still some short circuits and also some limitations still into the design and into the architectures of the battery. And so 3D printing is really an innovative way to obtain such architectures like this. So there is another objective to why using 3D printing as a tool to print batteries, and this is what we call in the mechanical engineering side of it. We talk generally about topological optimization. What does it mean? It means that we will try to reduce as low as possible, the material waste within the item. The weight waste, also the volume waste. And so here, I really like to take this example always. Just think 1 second about the Google glasses. So we all know the Google glasses, right? And if you take a look at the conventional design, you can see that the lithium-ion battery is a huge block in one side of the frame, right? And typically, thanks to 3D printing, what we could imagine is to make a topological optimization of it, meaning that we will have a shape conformable battery, meaning, for example, that we could think to really hide the complete lithium-ion battery within the wall frame of your glasses. So the battery will become the object. So here, Google glasses are just an example, right? But we could think about many other examples. I don't know, watches, for example, you will have the battery hidden into your wristband, etc., etc. So this is the second objective. And now I would like to move toward the third and last part of this talk, and which will be a little bit longer, of course, which is the work I've done and achieved during my PhD thesis, okay, on that particular topic of 3D printing of lithium-ion battery. And so what is 3D printing? So 3D printing, in the scientific field, we prefer to use the term additive manufacturing, and it consists in consecutive layers of materials that are deposited on top of each other. First step to do that, you need to draw the objects that you want to print. So we do that via computer-aided design software. And then this file, you convert it in, what you obtain is what we call a STL file. And this file is traditionally, as you can see here in the scheme, it's a mesh of triangles. And this is, taking into account the geometrical aspect of the objects that you want to print. This file, you will send it after to a second software, which is called a slicer. And here, typically, thanks to the slicer, you will put all of the printing parameters. So layer thickness, etc., printing temperature as well. Many parameters. And thanks to the slicer, also, at the end, we will divide your previous file into horizontal slices. This is what we call a G-code file. This G-code file, this is the one that you will send directly to the 3D printer. You had already put all of the parameters previously on this G-code file. And so you just reach the 3D printer, you click the play, you just press the play button, and that's it. It will start immediately printing what you asked him, okay, layer after layer. And so, of course, thanks to this layer after layer fashion, you can reach very complex shapes. So when I started my PhD thesis, that was in 2017, and so, we just took a look about all of the emerging 3D printing processes that were used at least a little bit to print lithium-ion battery. At the time, there was almost nothing in literature that was pretty empty actually. And so, I mean, here are some examples of some processes that were used, as you can see. So here, this is what we call the liquid deposition modeling on top left. Top right, you have the fuse deposition modeling, which is also part of the material extrusion family. And then you have here on top, on bottom right, you have stereolithography, and bottom left, selective laser sintering, for example. And so among these four, let's say, classical techniques, we had to choose one, right? And so we just did a small comparison, and directly, immediately, we excluded SLS and SLA because, you know, I mean, the plan of this project, of course, the main objective is to be able to print the complete lithium-ion battery in one single step, you know, meaning that you press your button and directly what goes off the print bed is your lithium-ion battery. And so to do that, actually, you need what we call some multi-materials printing options. And these multi-materials printing options are not widely available commercially for SLS and SLA. It exists, that has been reported in the literature, but it's very still complicated and not widely available commercially. And so far with these two techniques, you can only print, unfortunately, one material at a time. And so this is why, I mean, we just forget about that, and we rather focused on liquid deposition modeling and fuse deposition modeling, which are part of the extrusion family, material extrusion family. And why that is because these multi-materials printing options are indeed commercially and widely available. And so that was pretty interesting. Of course, then between these two different techniques, I mean, again, we had to make a choice, right? And of course, each technique, they have advantages, drawbacks, of course. And here, I mean, the main limitation about the liquid deposition modeling, unfortunately, is that you have, of course, an high limitation because it consists in some inks, so some liquids that are directly deposited through a syringe, here, as you can see on this small animation. And so this, due to the viscosity of the ink, sometimes you have some high limitation. Here, you know, post-processing steps are almost mandatory, like sintering, etc., freeze drying. And so this is why actually we just excluded this one, and we rather used for my PhD thesis the fuse deposition modeling techniques. Because here with that technique, I mean, what we wanted to achieve was to print the complete lithium-ion battery and don't do any further, you know, an additional post-processing step. No sintering at all, nothing. We just print and we obtain the battery. And of course, here, what was the main drawback about that technique is that we needed to make some composite filaments corresponding to different parts of the battery. And why is that? Is because if you take a closer look to that process, how does it work? You have typically, usually, a thermoplastic filament, which is used as material source for the 3D printer. And so this filament will be inserted into a heated nozzle. And by displacement of this nozzle into the 3 axes, okay, you will be able to deposit your material layer after layer and to obtain very complex shape, for example. And so, of course, I mean, if you want to print a battery, you need to first develop some composite filaments, right? And so that was my main task of my PhD thesis. That was to create these composite filaments for corresponding to each part of a classical lithium-ion battery. Here, I mean, using a liquid electrolyte. Okay, and so that's a huge compromise, of course, between mechanical performances and printability, and on the other hand, electrochemical performances. Because so here, sorry, we used as polymer matrix, we decided to use polylactic acid. So it's corn-based polymer, so it's like environmentally friendly. And PLA actually is the most used polymer in fuse deposition modeling, 3D printing application right now I mean, worldwide. And as active material for the electrode, as you can see, I mean, we kept very classical materials. So we used graphite as active material for the negative electrodes, and lithium iron phosphate, that we will call later LFP, as material for the positive electrodes. So, of course, as I said, I mean, this was a huge compromise between mechanical performances and electrochemical performances. And why is that? It's because, of course, I mean, if you make the formulation of your filament, okay, that you want to print, if you put too high loading of active material within the filament, of course, you will have, a filament that is very, very brittle, and so you will get the printability issues. On the other hand, if you don't put enough active material within your filament, what you will get is a filament with almost only pure polymer, okay? And of course, I mean, what you will be able to print, I mean, it will not be possible to use it as battery components, right? And so that was a huge compromise that we had to play with. And the final step, the final goal was to make a proof of concept and to demonstrate that thanks to this 3D printing technique, the fused deposition modeling, we were able to 3D print a complete lithium-ion battery in one single step, okay, in one single print. And so here is the scheme of the elaboration process I just followed to prepare, to prepare the filament, but also to print it, okay? So we first started with a slurry. So within the solvent, we just dissolved the polymer matrix. We add all of the different active material components and additives. And then we did tape casting. And after evaporation, we were able to obtain a film, a composite film. This film was divided into tiny pieces, cut into tiny pieces, and inserted within the hopper of an extruder. And by applying pressure and also melting, we were able to create composite filaments. This filament, last step, was used as material source for the 3D printer, and we were able to obtain many objects. Battery components. Here, for example, a picture of some electrodes that we printed. So as I just said, I mean, I just showed you this slide previously. As you can see, a lithium-ion battery is composed of many components, okay? 2 electrodes, separator, even some current collectors. And so for each component, we had to develop a different filament. So let's start with the negative electrode form. So before starting the development of our composite filament, we just took a look at what was available commercially. And we saw a commercial filament that was, here is the composition, as you can see, 92% weight percentage of polylactic acid, the polymer matrix, okay? And it was containing 8% of graphene. And maybe you know, but graphene can be used or considered as material, an active material for the negative electrodes. And so starting from there, I mean, that was kind of funny, okay, but due to the very huge amount of polymer matrix, of course, we were thinking that such a filament will be very easily printable, but not, not electrochemically active, at least not enough. And so what we rather try to do to improve the battery performances was to try to load a huge amount of active material. And so in that case, we try to load up to 70% of graphite, as you can see, and 30% of PLA, the polymer matrix. We did that just to maximize the electrochemical performances, while at the same time, just to, to keep enough mechanical strength to allow good printability. And so we tried to do that. So as I just said previously, I mean, we did the slurry, okay, within a solvent. Here we use dichloromethane to dissolve all of the components and mix it. We obtain a film, and then third step, okay, we try to obtain a filament. And here, unfortunately, with that particular composition, the filament was really too brittle and not printable. It was clearly too loaded in active material. And so we were thinking, okay, let's try maybe to incorporate an additives in order to avoid that. And what we did was to incorporate a plasticizer. That was the idea, to improve the flexibility of the filament and improve its printability. So starting from that same composition, we tested many different plasticizer, as you can see, polyethylene glycol dimethyl ether 500, 2000, acetyl-tributyl citrate, and propylene carbonate. So many complicated name, okay? So, but I mean, I will simplify it just after. And so for each plasticizer that we tried, okay, I mean, the goal was to determine which one we could use. And so right from the beginning, I mean, we saw that with propylene carbonate, there was an issue. Why is that? Is because we were indeed able to obtain a filament, but the filament that we obtained containing this plasticizer, PC, was becoming very brittle. And why is that? Is because when we perform differential scanning calorimetry, DSC, you can clearly see that here, you have a very broad peak corresponding to the evaporation of that solvent and so, to that, plasticizer. And of course, I mean, that was leading, to this evaporation was leading to the brittleness of that filament, and of course, resulting filament was not printable. So PC was discarded, and then we got also an issue with at ATBC and PGDME 2000. And why is that? Is because the final filaments that we were obtaining was kind of whipping, some drops of plasticizer coming out of the filaments. And so meaning that there was an incompatibility between the plasticizer, or chemical incompatibility between the plasticizer and also the polymer matrix. And so resulting filament, once again, I mean, it became very, very brittle, and once again, it was not printable. And so finally, we got lucky enough because we've got pretty good results with the last plasticizers that we tried, PGDME 500, polyethyl glycol dimethyl ether 500, okay? And of course, I mean, once you find the good plasticizer, you need still to make an optimization, right, about the content. So we tried different contents, okay, of that plasticizer within the filaments. And here the idea was to also tune, the mechanical properties of the filament. And so what we've done is we performed some tensile strength test on the composites, on some specimens. And so we just reached an optimum composition, and here is the final filament that we were, that was optimized with the plasticizer. And here you can see the final composition. So here, what is interesting is that this filament was printable at that time, okay? And you can see that the amount of graphite here that is used as active material within the, within the negative electrode was very, very high, 62% in weight, compared to the 8% that I showed you previously within the commercially available filaments. Okay, so of course it will maximize here the electrochemical performances of our electrodes. So here are some images, some SEM images of the filament, some cross-sectional image, and clearly what you can see is that the active material is really well dispersed within the polymer matrix without any doubt. But to obtain that, actually, that was kind of tricky because here, unfortunately, at least 100 grams of materials was required in order to get such homogeneous filaments. It's due to the extruders that we were using. Unfortunately, here, okay, graphite is not too expensive. So, even if we use 100 grams of materials, that's fine. But imagine it right now for the positive electrodes, other kind of materials. I was mentioning previously lithium iron phosphate, which is much more expensive, also more toxic than graphite. And so here, yeah, 100 grams of materials can be an issue. And so in future, it's better to try to kind of use a very small extruder and maybe also double screw to get a better and to ensure, very good homogeneity with much less material. So previously, as I just said, we got a filament that was optimized, with with the plasticizer, but we even went further and we continue our optimization by adding some carbon black or some carbon nanofiber, what I will call conductive additives, okay, generally speaking. And we studied their impact into the electrical conductivity so we have done that on films here. And so we tested, starting from our sample of references, okay, with the plasticizer optimized. We tested different amounts of conductive additive, carbon nanofiber, carbon black, some mix, etc., etc. And at one moment, okay, we obtained our optimized value, and that was corresponding to the optimized value from the electrochemical characterization that we got, meaning that we've got the best electrode performances with that particular ratio. And so here is that ratio, okay? And here, as you can see, I mean, we had to add 5% of carbon back here. Here's a TEM image, transmission electron microscopy image, and you can clearly see the carbon particles that are really well dispersed into the polylactic acid matrix, okay? And usually, I mean, to work efficiently, they should make a kind of percolation network between the graphite particles. And here, of course, I mean, as you can see, yes, it is happening a little bit, but I mean, clearly there is still room for a lot of improvement. So, I mean, it's working, but still room for improvement, of course. And finally, last but not least, I mean, we have performed some electrochemical characterization on it. So on some films, but also 3D printed discs. And here, I mean, that was just, you know, to show the proof of concept, meaning that what we just print was indeed working as an electrode. And so here, classically, I mean, so you have different manners to test that. I'm not sure, I mean, the students are really aware about how we perform electrochemical measurements. So here, just some reminder. So here in my case, I just tested that, you know, putting my working electrodes and testing it versus lithium metal and putting a separator with liquid electrolyte in the middle, okay? And I've done that within a swage lock. You can do that even in coin cells, in the push cells, I mean, whatever you decide, okay, in 1860, 50. So, I mean, you can do whatever you want, okay, for the cell, but here that was just a way to get some electrochemical performances from the working electrodes. And so here, finally, by doing this, so I'm not sure if the audience here is really familiar with that, so I will not, I mean, enter into too much details. That's not what I want to do here. But just what I wanted to say is that by doing such tests, indeed, we demonstrated that the electrodes that we just printed were indeed working as a negative electrode for classical lithium-ion battery. And this was a huge step for my group at the time, because I mean, that was maybe kind of first time that people were reaching such high loading of active material. And I think to this day, I mean, such high loading of active material within FDM-based electrodes and batteries, I mean, there is not a lot of studies on this. So it was quite promising at the time. And so, of course, I mean, what I just showed you was on the negative side, okay? But we have done exactly same work on the positive electrodes using lithium iron phosphate as active material, and also on, you know, we have developed as well a separator. So I will not enter into detail because it's exactly the same, but just I want you to understand that from the mechanical point of view, there are some changes, okay, some modification. Negative electrode and positive electrode are quite brittle, and the separator filament here was very flexible. And so, of course, I mean, when your goal is to 3D print the complete lithium-ion battery, the idea is to use the 3 filaments, you know, and of course, you need to adapt the printing parameters from your machine, right? Because depending on the mechanical strength, I mean, you need to adapt, and that was kind of tricky. Indeed, if you take into account, if you take a look at commercial filaments, these filaments are stiff, resilient, very hard, and so you can directly use classical printing parameters, classical, you know, temperature given by the reseller, etc., and you don't need to change anything. But if you take into account electrode filaments that were developed, they are quite brittle, and so unfortunately, doing printing, I was experiencing some breaks using, I mean, in the gears of the extruder, also nozzle clogging, and so it results, you know, in extrusion issues right from the start. Nothing was coming out from the nozzle, or also in the middle of a print, which was quite annoying. And so to avoid that, I had to make a lot of, you know, tuning the printing parameters and printer modification. For the separators, that was another issue because it was too flexible, and so we were experiencing another phenomenon, which is filament buckling within the gears. And so here, once again, I mean, some, you know, modification or optimization of the printing parameters were needed. From that, from these three different filaments, we printed independent discs, as you can see, for the positive electrode, for the separator, and for the negative electrodes. And we just stacked that, put that into a swedge lock or in a coin cell, and we just tried to make cycling of that. So here, we proved that it was working. Performances were very poor, but still, that was a proof of concept for us. And so we didn't stop here because, the next step was that we wanted, to obtain a complete lithium-ion battery into one single print, meaning that the electrodes and separators layer, our goal was to print it on top of each other's. And so, of course, that was also, a huge work because we had to implement an in-depth technical protocol with tuning of the printing parameters in the slicing software for each filament. So here are a few parameters that I put: filament load speed, nozzle and bed temperature, fan speed, flow ratio, and also reproduction. And so today I just want you to introduce a small video about that. So here is the logo of my previous laboratory that we wanted to print as battery. And so here the first step is to divide, the STL file the G-code file, into 3 layers corresponding to the 3 different filaments. So here you can see you are with me in the laboratory, right? And here's the printer, and I'm introducing the positive electrode filament within the printer. So of course, I need first, this is what I'm doing right now, is to purge the nozzle to be sure that what is coming out from the nozzle after is corresponding to my positive electrode filament. Okay. I've done the calibration of the printer, and right now, as you can see, I'm printing the first layer, which corresponds to the positive electrodes. So once this layer is finished, the printer will just go on the corner of the printer, just stop, and then I just need to press a button. Okay, I remove this filament. And so what's going next? Next step is, of course, to introduce the next filament. So the next filament corresponding to the separator here in that case, introduce it. Once again, purge the nozzle to be sure that what is coming out corresponds to what we really want to print, in that case, the separator, okay? And here, as you can see, we print the separator on top of the previous layer, which was the positive one, okay? Here it goes. And so once again, we had to remove the filament and load the last one, which was the negative electrode filament. So here, as you can see, what I'm doing right now is manually, okay? You can see me with my hand removing, putting the filament, etc. But actually, at the end, I don't have a video for it, but at the end, just before leaving France, we have done, automatic steps for it. So the filaments will change automatically. And that was another good result, actually. And so here, on top of the separator, last step is to print, of course, the negative electrode, as you can see in this close-up here. Once it's finished, the printer will stop, okay? Here you have your complete lithium-ion battery. So ready for the test, okay? Electrochemical test. Complete, yes and no, because there is still one component that is missing. Here, this is a liquid electrolyte. Indeed, here you have the 3 components of your battery, okay? This is here a transversal image by SEM of the batteries that I just printed, okay? In one shot, you can see that the layers are really well fused together. You have a layer for the negative electrode, a layer for separator, and a layer for the positive electrode. And of course, to make it a battery, it's missing, the liquid electrolyte that you must impregnate on top of it. And so this was soaked, this final printed piece object, we just soaked it within the liquid electrolyte, and then we performed electrochemical characterization to see the performances of the battery. Nonetheless, here you can see that the battery that we just printed, it was really dense, okay? And of course, this is an issue when you want to print a lithium-ion battery. When you want to cycle a battery, because the liquid electrolyte must be very well impregnated, okay? And so we have done electrochemical performances of this, and unfortunately, they were really limited due to the poor impregnation of the liquid electrolyte. And so we went even further, and we took advantage actually about the 3D printing capabilities and the 3D printing software itself. And so here we try to introduce some very classical 3D printing infill patterns that are automatically generated by the 3D printing softwares. And we try also to play with what we call the infill density, okay? And by doing so, for the separator, as you can see here, we were able to create some cavities, some caves. So here on the right, the image B is actually a cross-section image of the 3D printed discs, okay? And so here, I colored it. So in blue, in top, it's the positive electrode. At the bottom, it's in red, it's negative electrode. And here in gray, it's the separator, if you didn't understand. And you see, we created some caves, and this was allowing actually the liquid electrolyte to be very well impregnated. On top of it, you can see that I just put a small, tiny, very thin layer of separator additional, and that was just done to get, to don't have any short circuits while 3D printing. And so we got to a proof of concept actually with this one-shot printing in one-shot battery, and performances were still limited, but it was working, and that was a huge advance for us. So of course, what I just printed here, as you can see, is just planar. Okay, it's still planar, and as I told you at the very beginning of my talk, the idea is to even go further and to print some three-dimensional architectures of the battery. So here you can imagine in blue the positive electrode, in red, for example, the negative one, and in white, for example, the an electrolyte or separator, a separator. Yeah. So and I've been working as well, and just that's a preliminary work that I've done with a multi-materials option. And so this is the next step right now that I'm working on, is to use a multi-materials unit. So here in that unit, you can introduce up to 5 filaments and print 5 filaments at the same time. And so the idea is to print some very complex shape here. So I've done that with commercial filament, as you can see, and next step is to do it with my composite filaments, which are unfortunately much more complicated to print. Okay. So thank you very much for your attention. I would like to thank again the organizers and Chardin University for inviting me. And you can contact me by email. And also, if you are very interested in that topic, please don't hesitate to follow my professional accounts in LinkedIn and Twitter. Thank you very much, and I really look forward to answering your question. Thank you.
Thank you for such a wonderful and very interesting topic, Dr. Alexis. We received a couple of questions. I request you to,
sure, I open the
interact. One of the question is, which apparatus is used to cut electrode film into small filaments?
So I did that manually. It's simple. So I just type cast, I use the Dr. blading technique. And then this film, I just use a razor blade. I cut it myself, like 3 meters per 3 millimeters per 3 millimeters. And then I just inserted it into the hopper of the extruder. So I know there are some other techniques that you can use, to get some pellets, etc. I didn't do that, but this is another way to do it. Yeah.
Okay. A second question is from Dr. Sarojini. She asked you to suggest suitable 3D filament with good thermal conductivity for the 3D printed heat sink to cool lithium-ion battery. So
I didn't work with I didn't study materials with, I didn't do filament with that, with, materials having good thermal conductivity. But nonetheless, I've done something recently. This is maybe of interest for the person who asked this. Here, just a summary of some publications that I've been working on recently, and on that topic. And here in Frontiers in Energy, we just recently published. That was a silver-coated copper filament. And so, of course, here, we were able to print that, as current collector for the battery. And so, yeah, here I think I mean, copper, I'm quite sure it has a good thermal conductivity, if I'm not wrong. I mean, at least much better than the other filaments that I produce. So this is something, but definitely, I mean, with 3D printing and the various filaments that you can do, you can imagine to print, you know, to add whatever materials you want on it and to print whatever you want. Yeah, so definitely to add within a polymer matrix some materials having, you know, good thermal conductivity for some applications could be very great.
Okay, thank you, Dr. Alexis. Thank you for such a information rich and such an interesting upcoming technology for the preparation of lithium-ion battery and its role, the role of 3D printing in this regard. Thank you very much. I hope we can invite you during offline conference in future, and certainly we'll collaborate with you for further research. Thank you very much.
Sure. Thank you very much, sir. Thank you very much once again for the invitation, and particularly to Professor Minal Gupta, who contacted me. Thank you.
Thank you. Thank you.
Thank you. Thank you, sir.
We have our next speaker. Our next speaker is Dr. Seema Garg. She is from Institute of Applied Science, Amity University, Noida. She is working as an assistant prof there, and the title of the presentation is Green Visible Active Material for Environmental Remediation. So, Dr. Seema Garg.
Yes, good morning, sir, and good morning to all of you. Thank you, Dr. Meenal and Dr. Yogesh Kumar from DU, those who have given me opportunity to deliver my talk on green visible active photocatalytic material.
Yeah, so before I introduce, ma'am, you start your talk, let me introduce you for our participants. Dr. Seema Garg, she received her MSc in 1998 and PhD in 2003 from Agra University, UP. She began her career in 2000 as a guest faculty for the classes of analytical chemistry. She then moved to Amity University in 2011 and is currently head student affairs AIAS AUUP Noida. She has been chairperson NTCC AIAS. She has experience in teaching BTech, BSc, MSc and PhD students. She has a career spanning of more than 20 years. She has a credit 12 patents and a number of publications in journal of repute. For example, Royal Society of Chemistry, Elsevier, Journal of Colloid and Interface Science, Separation and Purification Technologies, Journal of Industrial and Chemical Engineering Chemistry, etc., and MDPI journals with a H index of 10 and I index of 13, with a total impact factor of more than 10. She has completed a project as a principal investigator in DST NRDIO sponsored bilateral Indo-Hungarian research project with a total funding of 1.74 crore. Now she has again got approval of DST NRDIO sponsored bilateral Indo-Hungarian project with Dr. Praveen Ingole and Dr. Seema Sapre, IIT Delhi. She has been invited as a speaker to present her groundbreaking research in many conferences, nationally and internationally. So, welcome to Dr. Garg. You can start your talk.
Thank you so much, sir, for the introduction. So, the topic of the talk is green visible active materials for environmental remediation. Now, as you all know, in the recent years, the rapid industrial growth and the population causing the problem of the pollution. And this is actually the major concern in this whole world, not in only in India. Even at low concentrations, some of the organic pollutants could be a serious threat for the environment. There are many techniques to solve this problem, as we see the conventional techniques, precipitation, coagulation, adsorption, centrifugation, but these could not solve complete problem. You can say these cause secondary pollution. So the problem is major and we have to think to solve this issue. So for that, the work can be done on photocatalysis. So photocatalysis is a technique that is also called green technique. It is the technique in which light is used to absorb the light is used and the material is activated and produce electron and holes. And these electron and holes are mainly responsible for degrading the pollutant. Photocatalyst is the substance which can modify the rate of reaction after absorbing UV or visible lights. So you can see here advantages of photocatalysis. You know, this is the green method. So the many advantages of photocatalysis is there. The complete mineralization of almost all the toxic contaminants which are present in the wastewater. If byproducts are formed, they are also environmentally friendly. Easily available atmospheric oxygen is used in this process. Photocatalysts with semiconducting properties are economic, non-hazardous, chemically stable, biologically and chemically inert, and reusable. You know, UV light, generally the photocatalyst we use, and if you see the literature that is related to the UV light, and these are generally used zinc oxide and TiO2 photocatalysts because of the several properties which we need in the material is there in these TiO2 and zinc oxide. But the problem is they are UV active photocatalysts. So I'll go to that topic later. So UV light with lower energy is generally used for the reaction, and besides solar light energy can also be used. The photocatalytic material with low price is comparable with activated carbon adsorption method for intermediate and large capacities. So you can see the mechanism. How does it happen? The pollutant gets absorbed on the outside surface area. The photocatalyst absorbs the light and the electron and holes are separated. You can see oxygen is converted to superoxide ion and holes are absorbed by the water and form OH free radical. So these species, superoxide ion, OH free radical and holes, generally responsible for degrading the pollutant by the reaction. When you see the TiO2, when UV light is incidented on the material, these electrons and holes, again I have shown it here, superoxide ion free radical and OH free radical, and these degrade the pollutant problem. Now, so the advanced features which we need in the photocatalyst are they should have high porosity. If it is having large surface area, for getting more efficient results, and for the results the photocatalyst should have these properties: porosity, surface area, band gap narrower, smaller size, enhanced separation of electron hole pairs. But the problem is if they have narrower band gap, they can absorb visible light. Because of the visible light ranges, wavelength range is more, that is more than 400 nanometer, and the band gap is lower in that case. But the problem is the electron hole pairs generally combine in this case. So the researchers generally prefer UV active material. But if the band gap is lower and we can stop the combination of electron and hole pair, then the next problem means like the efficiency can be enhanced. So visible light driven photocatalysis for wastewater treatment. Now if we see the visible light, which is 46% present in the solar and only 4% UV light is present. But the problem is we need these properties: high surface area, economic, non-toxic, safe, and the property like they should have the property to absorb the light, visible light, and the electron hole recombination should be stopped or minimized. So the thing can be solved by the bismuth-based semiconductors, and they are better photocatalysts if we compare it with others. So because of their low toxicity and abundance on Earth, if you find these bismuth oxyidate, titanate, oxide, tungstate, calcium bismuthate, vanadate, oxycarbonate. There are many bismuth-based materials are available in the literature and people are working on. But we found that bismuth oxyhalide is superior material if we compare it with other bismuth-based materials. So they have actually the layered structure. Bismuth oxide ion interleaved by double slabs of halogen atoms. And because of their layered structure, there is low possibility of the recombination, but the electron hole are separated because of this layered structure. Moreover, we will modulate the property also by using some green methods. I'll I'll come to that point. Now you can see the bismuth oxide, which have been prepared by different methods like solvothermal. In that, solvents were used to prepare the material, and the hydrothermal high temperature was used to prepare the material, and the activity was obviously good. So the method is solvothermal, hydrothermal, precipitation method. Many methods are given. Now, we thought for our Indo-Hungarian project, we have completed in 2020 first project with Hungary, and in that we introduced that if we use the green leaves or plants, we take the help of these to prepare the material, and we stop the use of the solvent which are very harmful. So then the green method, that is called photocatalysis, can be more green. So we took this, we worked on the green leaves, and we got very, very good results in case of chlorides, bromides, iodide. Even we turned that fluoride, which was UV active, now come to the visible active range. And then the composites were formed, immobilization was done. In all aspects, we found that this is actually the best material among all visible active materials. So you can see here the results. And bismuth oxychloride, which was formed by the different leaf extract, to get that all the leaf extract have same properties almost, or they are different. So in that case, the bismuth oxyhalide was prepared by hydrolysis method, and the method was repeated, only we use here plant extracts at same temperature, same conditions were given. And the SAM image is of bismuth oxychloride prepared by the hydrolysis method, and the B, C and D images are of the material which was prepared by as a directa indica, Ocimum sanctum and Saraca indica. So 3 leaves were used to prepare the material at same condition, and in these all 3 we found that the plate, actually bismuth oxychloride has plate-like structure. But now here, when we used the green method, we gave the name as green method because we replaced all the solvents and then used plant extracts. So that found that these all have the nanoplate-like structure now. So by the TEM images, it was confirmed. HR TEM images, we found that the lattice fringes at 3.344, 101 and 101, and the spacing between 0.344, 0.335. So it confirmed that yes, these are BiOCl, nothing else. Hai na? Now by the XRD, you can see in the case of this is the chemical one. Then this is the Saraca indica and Ocimum sanctum, and as a directa indica, and in all you can see the peaks were broader. So by Shearer equation, we found that these are now nano. So the plates were smaller. So by all the characterization, our results were going in the same direction, that we have done something good with the material as a green. So here, when we test the band gap, that was also smaller. So this is next good opportunity for the material to get higher efficiency. In the case of FTIR, we found the peaks, extra peaks we got in the case of the material which was prepared by the green method. So these are responsible for enhancing the property, for separating the electron hole combination. Or now by the XRD and by the XPS, again we found that the results are going good. And then these are the photoelectrochemical studies were also done to see the electron hole recombination by our IIT partner Praveen Ingole professor. Now we found that in the chemical case, the recombination is more by switching the light off and on. Then here we got that chemical one is this one, red one, and these are the green one, blue, green, and this red one. So showed the good electron hole recombination found. Here by the Nyquist plot, you can see the smaller circle by the green one and the bigger circle of the chemical one. By photoluminescence, again we found that the recombination is smaller. And then we checked that which species mainly responsible for the photocatalytic activity. So for that, we did the experiment with sodium oxalate for getting the results of holes, if these are responsible, isopropanol for getting the results for OH free radical, benzoquinone for superoxide ion free radical, and found that all these species intermediates are responsible for the degradation of the pollutants. Here we did the study with methyl orange. So this is the percentage degradation of methyl orange. So here you can see the results. of photocatalysis, and this is the kinetic study which was done, and then found that this shows the pseudo first order kinetic model. Here we showed that 100 mg is the optimized limit. The study was done in the dark and then in the light. So the light is irradiated and found within 90 minutes the maximum degradation was found. Here for the chemical one, you can see the result with chemical one. The optimized limit was same with chemical and green one. And this is the N, T, and A different leaf extract, and almost the result was similar, but with as a direct indica, that result was maximum is 91.8. This is 7.1 and 88.9. But with chemical one, you can see the difference. So almost all leaves have same constituent, and they are working to enhance the photocatalytic activity, to enhance the material property and morphology changing, and the features going towards the good activity. And this is the chemical one, only 70.3%. So now with HPLC spectra, we found that any we did this study with not only methyl orange but with bisphenol A also, to see is it able to degrade bisphenol A also. This is very major pollutant and the big problem. So then we found that BiOCl-N also degraded, and BiOCl this is the N1 and this is the chemical one. So this we found in both. The degradation was done within 600 minutes in bisphenol A case, but the 4-hydroxy acetophenone was appeared in small amount, but this is not as harmful as bisphenol A, but it is actually safer. Now the mechanism was given for this in the both cases, chemical and green one. By then the paper was published in Ecotoxicology and Environmental Safety. So in this journal. Now, we did the study with BiOBr because we wanted to know, is this only helping for BiOCl or others halides also? So then again, the chemical one, this is the hydrolysis method completely. And then with same condition, when we used the isodirected indica, because we found that the result was best in that case, and found the nanoplates were obtained by XRD, we again found that the broader peak. So this shows the nanostructure. Surface area was enhanced. That was 14.7 and now 79.5. So approximately 5 times surface area was enhanced. Then the photocatalytic activity was done, and with phenol now we checked it with, and we found that the result was almost the 100 mg is the optimized limit in both chemical and green one result is more. These are the chemical one results. Scavenger studies were done. All species were found responsible for the degradation, and the pseudo first order kinetic model was followed. So for both chemical and green one, all the species were responsible. Now, specific surface area was detected by BET and found the 5-6 times, like the surface area was enhanced, 13.938 to 79.592. So the photocurrent response and the electrochemical studies were done, photoluminescence, Nyquist plot, and found the same results, that BiOBr-G was better, much better than chemical one. Then we did the recyclability studies also. So not only one time, we studied the same photocatalytic activity 5 times, and all times the result was similar. And then we did the SAM study also for the samples after completing 5 cycles, and almost the similar morphology we saw of the material. That is HPLC was done, and mass spectra, and found the hydroquinone peak was appeared in a little amount. So that is not a problem if we compare it with the phenol. Then materials, the journal, this paper was published. Now the BiOIE, the studies were done, and a bigger plater were converted to the nanoplates. Then the XRD was done, and this paper was also was published in RSC Advances, and that 73.45% to the 95.91% methyl orange degradation was reported by the BiOIG 95.91 and chemical 73.45, and all the studies were done like the previous studies, and the scavenger studies were also done, and the rhodamine B and methyl orange 2 dyes were used to degrade by BiOI. Now next is, then we thought, okay, we will check with fluoride also, BiOF, because it is actually UV active material. Its band gap is 3.2 3 electron volt, 3.2, 3.3. Then we found that, and one more thing we wanted to know, as the plant extract is having which constituent which can be responsible for the properties, for enhancing the properties. For that, there are many constituents which are present in the plant extract like quercetin, ellagic acid, gallic acid, anthocyanins. But here, then we prepared the solution with all. Now I am showing the result in which I got the maximum potential and good properties and better one. So here we prepared leaf extract solution, quercetin solution. So quercetin we found is mainly responsible for enhancing all the properties. So, and one more thing, we prepared one or more BIOFC with the ethylene glycol solvent to see the results, what is the difference. So here when we found that A, B, C, D, E, F, these are the chemical, this is the chemical one, and these B, C are the with the quercetin and with the plant extract. So we found that quercetin and plant extract have almost same particle size here. And when we did the studies, in the case of the blank methylarine, the no photocatalysis was reported. And then the chemical one, this red one, and this 0.025 molar, this is the degradation, and the quercetin 0.05 molar and 1 molar. We prepared 3 solutions of the with quercetin and the plant extract. You can see the plant extract is having little bit more property because not only quercetin, other constituents, but almost the same properties we found with the quercetin. So the results were shown like that, pseudo-phosphokinetic model, the same, and then the degradation of benzotriazole was done here. In the 540 minutes, almost all the degradation was done, and 3-aminopropanol peak was extra, it was appeared over there, and then this was confirmed by HPLC and mass spectra, and Journal of Photochemistry and Photobiology, A-Chemistry, the paper was published last year. So now the constituent which are responsible can be gallic, anthocyanin, ellagic, and quercetin, but quercetin is mainly responsible for the properties. Now the next is fabrication of green bismuth oxyhalide based composite, means like we have done the work with the all bismuth oxyhalides, but now we thought, okay, if we'll prepare the composites, the property can be enhanced like more. And if we compare it with our earlier work, so we thought for that, and then we thought if BIOI is giving whatever the percentage degradation, if we'll prepare the composites and we add something for the composite to only separate the electron hole more, because more electron and holes are there and more property will be enhanced, more activity will be enhanced. So for that, not only plant extract, that the composites can also be prepared by using plant extract, not only BiOBr and I. So we have done it like BiOBr X, I1 minus X. In that we changed the percentage, and then we found that BiOBr 0.2, I 0.8 is having maximum property, maximum the photocatalytic activity. So here we saw that A is the chemical one, then B, C, D, E, F. These are the green one, but with different concentration of Br and I, and GH is the TEM images, and this is HR TEM images, found the XRD images. You can see the broader peaks. So found that now I'll come back. Now this mechanism, possible mechanism was given here. Here this is the azadirachta indica leaf extract with its constituents. They are quercetin, gallic acid, ellagic acid, anthocyanins, and then bismuth nitrates. What process is going on? This is making the complex between bismuthine and leaf extract. So we gave this probable mechanism that what can happen here with the leaf extract. Actually, they are making the complex because the leaf extract is making the particles smaller. So it can happen because of this. And then when the KBr, KI, what is happening with it? It is forming the plates, nanoplates, and then self-assembly, it's making these kind of plates, bigger and smaller. So here the photodegradation of amoxicillin was done, And here we found that this is the blank one, and these are the G minus, this is the different ratio we did this experiment with. So this blank and the chemical one and the green one we tested, and then the pseudo first order kinetic model, and this is for the different material this was given, and then this LCMS, and this is the HPLC, and this is the LCMS which was done, and found that amoxicillin is giving the different one more peak, that is amoxicillin S oxide, was confirmed by the mass spectra. Then again the electrochemical studies were done and found the same result, and by Seeley we found that the leaf extract is having electron accepting nature. These ESR studies were done, the superoxide radical, hydroxyl radical were there, and then percentage degradation of methyl orange and amoxicillin was done, and found that for methyl orange almost all species were responsible, but for amoxicillin degradation, holes and superoxide and free radical were mainly responsible. And the photodegradation mechanism was given for the composite, and then these are the composites and the leaf extract, the electron accepting nature, and then this is making the interface, and electron hole recombination is more in this case, and that's why the properties are more enhanced. This was published last year in Journal of Colloidal Interface Science, approx 7.5 impact factor. So this is it. So now the next. Now the problem is we have prepared the material which is having, according to us, the best property, and we have selected the material. Now we thought, how can we recover the material? What is the process by that the material can be recovered? Because in the lab, this is the problem every time, the recovering. How can we recover the material? Centrifugation, and then again filtration and all. So for that, if we immobilize the material, then the material can be used very easily, and then the pollutant problem can be solved. For that, we use two substrates, because we need the substrate also, and then the particular substrate we use that ceramic fiber and carbon block. The ceramic fiber was provided by my Hungarian counterpart, Professor Clara Hernadi, and this carbon block was supplied by Active India Carbon Limited, that is in Hyderabad. So we did that and used that for different degradation. Now, the immobilization of the material was done on this ceramic fiber first. Then we prepared the material in the lab, and then this is blank ceramic fiber. It was appeared like I have shown it here, the paper which was immobilized with different bismuth oxylides, chloride, bromide, chloride, bromide, and iodide. And then the SAM images were taken place of these, and then found the BT surface area of different material. Surface area was enhanced of all, and like the different material have different surface area, and this was increased if we compare it with blank. And the photocatalytic activity was checked of all. Then you can see here the results. So this is the blank ceramic fiber. Obviously, this is having some adsorption property, which I have shown here. This was done with ampicillin and bisphenol A, 10.1 and 7. But with ceramic fiber, which was immobilized with Cl, that you can see that 14.2, 11.1 was the adsorption, but this is 63.7 and 56.8% degradation in visible light. When we check it with BiOCl ceramic fiber plus, means like in the combination of all, then we found the result in this way. When you see this, we made the combinations of Br, then I, then CLBr, CLI, IBr, and they all three in combination. When we took all three in combination, we found the better result, 93.2 and 85.8% degradation of bisphenol A. Then the recyclability was done, and then we took the images of these samples, and the SAM images were almost similar. So we found that it can be used several times for the degradation, and the Ceramics International paper was published in. Now that the next thing is done with immobilization of green BI on 2D carbon block. So that actually this was prepared by our industry. We provided the sample, and then they did this. Now we use the sample, this carbon block for the checking of the photocatalytic activity, and then we characterize the material also. This is the carbon block, and then when we immobilize the material, you can see here the material has been immobilized, then surface area was enhanced, and this is the band gap which was lowered. Now then we did the degradation of blank amoxicillin, this was the straight line we got. And then accordingly, blank carbon block is having adsorption property, but then it got straight. Here you can see the degradation, photocatalytic degradation, and a 0.1, 0.5, and 1% gave the maximum result. So here also blank ampicillin and then carbon block, and then we found again 1% carbon block gave the better maximum result if we compare it with others. So this is the HPLC was done and found amoxicillin was converted to amoxicillin S oxide, but ampicillin was converted to penicilloic acid, 2-hydroxy-3-phenyl pyrazine. So these are not so harmful and very small amount these were, and then mass also confirmed the same. So by the different characterization technique, it was clear that this is BIO, this was immobilized on carbon block. And now this is not so clear image, but I think you can see these are the XPS data, bismuth oxygen iodide, and this is carbon, and this is survey of that. And these are the FTIR results, in that we found that plant extract which is present in that material gave its own peak. And here the XRD, and so it was confirmed that in this case the material is better. And now you can see here the mechanism which was given for amoxicillin and ampicillin degradation, and these byproducts were formed. This was published in Separation and Purification Technology last year. So now these more papers were published on the review on BIOX nanomicrostructures in journal Nanoscience Technology. This work was done by my student Nikita Sharma in Hungary. She is doing PhD from Hungary under Professor Clara. She's my collaborator from there, and she is published on hydrothermal synthesis. She did the work in the by taking the temperature here, more temperature by the method hydrothermal. So they are preparing the using hydrothermal method. Here we have used hydrolysis methods, green method. So the one more paper by Aniko Bardos, and she's also our collaborator with from Hungary and doing PhD under Professor Clara. And that quercetin, then we did one more work because of the limitation of time I did not show here. This is quercetin mediated, then we prepared BIUIQ and BIUI silver. So because we need that antibacterial activity also, because in the water we can see the germs can also be there. So we prepared BIUI silver, and this paper was published in Journal of Alloys and Compounds. And here we have shown the antibacterial activity with many different bacteria using. So here the one paper now in 2021, this recent enhancement in invisible light photocatalytic degradation of organochlorine pesticide. This was a review, and recently it has been published. This is also a review Journal of Industrial and Engineering Chemistry, 5 impact factor. This is done by my student, PhD student. Now she has started work on the different bismuth metal oxides, bismuth, not only bismuth oxyhalides, but bismuth based metal oxides, to see the property of these. And we want to go in deeper way. So to see this, she has published one review of environmental remediation and clean energy production. And one more paper, size controlled platinum over mesopora. So to use the next work on thermal catalysis, like carbon dioxide hydrogenation, we've started work on. And this was done by our collaborator Andras Sapi from Hungary. And these are the patents which have been filed on photocatalysis. So I filed 11, 12 patents, but on photocatalysis filed 5 patents. So these are. And this is my research group. Professor Clara Harnadi from University of Szeged, Hungary, and Professor Samir Sapra from IIT, Professor Ingole from IIT. She's Professor Christina, and Aniko Bardos working, like she's working in this field, but she's PhD student. He's Mohit Yadav. So he was my student, and he has done work under this project, Indo-Hungary, which was sanctioned in 2016 October. And now he has gone for a postdoc position in Hungary under Professor Andras Sapi. Now he's student of Hungary. So he's Dr. Amrish Chandra, my husband also, and he's also my collaborator and working with me, and he's patent agent also. So he's a government patent agent, and she's Dr. Tunde Alapi and Miss Nikita. She was earlier ex-student of MIT actually, and now she's doing PhD from Hungary under our project, collaborative project. So this is the like when I visited Hungary. So I visited Hungary 3 times. So third time when I visited, then I got the certificate of appreciation as the principal investigator of exemplary collaboration during Indo-Hungarian joint program by University of Szeged. And this is actually the achievement which I found that yes, I have got something during this project. I have got many things, but this is the certificate of appreciation. So yes, it's really good. So these are the international collaboration which I have from Brazil with Marcia Marx, from Italy, Marcia Lucia, Russia, Professor Lebedev, UK, Dr. Janwang, Germany, Professor Glazer. I have many collaborations, but these are the collaboration in these persons I'm working with, working in a different field and doing work. Okay, thank you so much for patient listening. So I look forward if you have any questions.
Thank you, ma'am. Thank you for your such a informative and nice presentation. Ma'am, I have a couple of questions. One question is how cost effective is the process, and how much it is possible to commercialize this process for real time bioremediation?
Okay. Actually, this is a very nice question because it's a need of the hour also, I'll say. This is actually the cost-effective process because I have replaced all the solvents and chemicals which are costly, with you by using only plant extract. One thing. Second thing, I'm not only replacing the solvent and chemicals, I enhance the property also, photocatalytic activity. So the one thing is this is very cost effective because the costly chemicals and moreover hazardous chemicals I have replaced with only plant extract. Second thing, I'm thinking for the commercialization of this my process, and I have prepared a small video. So if you will allow me, I can show you. This is the process.
Certainly.
Okay, surely I'll show you. I hope you all can see.
Oh, ma'am, kindly share the video.
I have not shared. Wait a minute.
No, you can see at the bottom there is a share screen. So
Yeah.
I've done
Industry under DST project. Bismuth oxides and silver have been impregnated into the carbon.
So this is the product which we have designed in our lab. In this, we have impregnated our bismuth halides in the carbon block, and I'll show you.
The material which has been used in the process are prepared by green hydrolysis routes, thus eliminating the use of hazardous solvents. Much higher efficiency of these nanomaterials recorded due to higher surface area, increased porosity, and lower band gap. This prototype solves two major problems of the photocatalytic material. Firstly, since the nanomaterials are difficult to retain and recover, this problem is solved by impregnating the material in the carbon block. Another challenge of preventing the recombination of photogenerated charges has been solved as multiple interfaces have been generated in the composite. Thus, inhibits the recombination of electron and hole pairs, and therefore more photogenerated charges are available for the photocatalysis process. The patented material is highly efficient in degrading the recalcitrant organic pollutants. Let me show how the system works. I am pouring the contaminated water, it is colored dye solution, into the patented prototype, and as the liquid flows down in the presence of light through the column, immediately clean water without any contamination is obtained. The process is efficient enough to degrade the recalcitrant organic pollutants present in water like antibiotics, pesticides, phenol, bisphenol A, benzotriazole, and all dyes. If industry will pass their contaminated water through this prototype before dumping the water into the mainstream, then water pollution problem can be solved.
So this is the short video which shows that we want to commercialize the process, but I want to do more studies in this process. So still
Thank you, ma'am. It's very interesting, and is it possible to also photocatalytically remediate that azodye also? Like
yes, sir. Azodize I am doing the work on methyl orange and many dyes I have worked on, and I'm trying to degrade the antibiotics, bisphenol A, benzotriazole also. So I found that success also in this field, and see how can I go ahead and how can I give this product to the industry or the common people. So we are waiting for a few more studies in that.
Thank you very much for such an intriguing and such an interesting topic. I hope we can have some collaboration, and in future we can work together.
I'll be more happy because I believe if we have collaboration, then we can go ahead. Otherwise, single person cannot do anything. So yes, so I'll be more happy if anyone wants to collaborate with me, or anywhere I can help in any like your work. Thank you so much.
Thank you.
You are most welcome.
I hope in future for offline conference we can invite you and they can come up with lecture. Thank you very much.
This is my phone number I have given in the chat box. If anybody wants to contact me for anything, I'm happy.
Ma'am, I have one more question. Did you use any biocomposites for sensor application?
No, sir. No, I have not done this. If anybody is interested or they can think of, we can use it.
Oh, thank you, ma'am. Thank you once again.
Thank you so much, sir, for inviting me. Really, thank you so much.
So we are about to finish the first session of our last day in this workshop. In the next session, we will have two more speakers, Dr. Shubhendu Bhandari from Maharashtra Institute of Technology, Aurangabad, and Dr. Priyanka Maheshwari. We'll start our session sharp at 3 p.m. So till then, please, I request all of the participants to join at 3 p.m. Thank you. Bye.